Back in our notebook, let's extend our linear regression analysis to include multiple independent variables and implement a multiple linear regression. Now we know that when we consider multiple independent variables, we have to be very careful about multicollinearity. Multicollinearity arises when we have different independent variables that are correlated with each other. And so it becomes very, very difficult for the linear regression model to tell the individual effects that each of those independent variables has, because it cannot keep the other constant. The very first thing we're going to do is first to qualitatively assess multicollinearity using plots. And for this, we're going to bring back for the third time our pair plots. So let's give this a second to run. Okay. So before we had been focusing on this bottom row right here because we were interested in how the independent variables correlate with our dependent variable. Now we're interested in this section up here, which includes the pairwise correlations or relationships between the independent variables themselves. And what we're looking for here is we don't want any sign of a linear relationship. And happily, it looks like all of these pairwise scatter plots show no linear relation whatsoever, meaning that all of the independent variables are not correlated. So that's good, and in this case it is so clear-cut that we could potentially move on, but in some cases it might not be as evident that there is no relationship between independent variables, so we might want to quantify the strength of that relation between the independent variables. And we do that using correlation. Remember, correlation is a measure of how two variables move together. It can vary between +1 when there is perfect correlation, and when one increases, the other increases, and -1, which is perfect negative correlation, which means when one increases, the other one decreases. What we're looking for is close to zero correlation, which means there is no relationship between the two. The first thing that we can do is just display the correlation matrix. So we're going to call the core method of our data frame. And this shows very much like the pair plot, we have all of our variables as rows and all of our variables are columns as columns. The diagonal this time is always 1 because a variable is always perfectly correlated with itself. And what we are interested in is in these values here. So this is our dependent variable, so we care about the independent variables within themselves. And we see that none of these values seems to be close to 1 or -1. Now this is quite a lot of information, and it can be difficult to digest, especially as the number of independent variables increases. So we would like to be able to see the results of this correlation matrix in a very visual way. So for that, we're going to take the result of our correlation matrix and we're going to display it as a heat map. So we're going to take the same correlation matrix and we're going to display it as a heat map. And I want to keep the numbers on, so I'm going to pass in this extra parameter called annote for annotations, and I'm going to set it to true. Excuse me, I mistyped this. This is a heat map. And now we can see the same results as we saw in this matrix in a visual form. So we have all of the ones along the diagonal because all of the variables are perfectly correlated with themselves. And again, we want to focus on these 1, 2, 3, 4, 5, 6 variables values here, which are the independent variables with themselves. And we see that they are all relatively close to 0. A good rule of thumb is that you should start worrying if you see values greater than plus 0.6 and smaller than minus 0.6. In this case, they're all really, really close to 0. So we're happy to say that none of these independent variables are correlated with each other, so we don't have to worry about multicollinearity, and we can continue with our analysis.